my name is Christopher James Kosick.
And I am Jose Ignacio Rodriguez Labra.
And we'd like to thank you for taking the time to view our senior design presentation, which is a multi-channel PPG system for medical applications with Dr. Masoud Atashbar as our project sponsor.
We give special thanks to our advisor, Dr. Atashbar, for all the support, including all of our lab mates in the CAS lab that helped us in the project. First, the peripheral artery disease, otherwise known as PAD, is an abnormal narrowing of arteries. Current instruments for detecting PAD are expensive and not widespread, and diagnosis is highly important since patients with PAD have a high risk of death from cardiovascular disease. This affects Americans millions of dollars in buying the medical equipment for diagnosis and potentially increases risk for those who don't get early treatment. It is difficult to screen for PAD when someone is asymptomatic or have pre-ulcer conditions. A method for diagnosing PAD is by measuring the toe branchial index, which is the ratio between the systolic and asystolic toe pressures. But this method is not widely available. Meanwhile, wearable devices are focused on general fitness, not diagnosis.
Our project concept is centered around extending the use case of existing wearable devices that, as mentioned by Jose earlier, are targeting fitness and kind of health markets. Specifically to address PAD and other blood circulation diseases, we know we need a system that is obviously capable of doing this continuous monitoring. And in addition to that, we need multiple types of sensors so that we can filter out a large variety of live environment variables. And we wanted to include a redundancy in terms of the type of sensors that were going to be used in the system. To explain a little bit further, we would have multiple, whether it be PPG sensors or ECG sensors, redundantly placed in a local area so that we could get data, blood data, from different various points as we're applying them. And the last thing about the system is that we knew it had to be modular, meaning that we could implement it into a large number of physical configurations. For example, a shoe may be a really common one if we wanted to get blood readings from a shoe, but also into a glove or shorts or other kind of physical configurations, as well as system configurations as shown in the graphic there. There's a lot of work towards body area networks. It takes a lot of different devices, and they can all communicate and kind of create a larger picture of health of the individual. So to summarize and start developing some technical requirements of the system, we knew it had to have some form of wireless communication, multiple sensors, robust handling of various environment details, a soft real-time response. We really wanted to make sure that we were getting live data across, and it needed to be power efficient. And to achieve those needs, we decided to use the Bluetooth Low Energy 4.1 protocol because of its lower power consumption for our wireless. And we knew we were going to implement an inertial measurement unit that kind of integrated together an accelerometer, gyroscope, and some temperature readings. And we decided to use photoplethysmography for our actual blood data detection, which Jose is going to get into the explanation of what exactly is photoplethysmography.
PPG is short for photoplethysmography. PPG sensors use light transmitters and light sensors to measure changes in light absorption. From wearable fitness devices to hospitals, use PPG sensors to find cardiovascular metrics in individuals. Why did we choose PPG? PPG sensors are non-invasive, which means no blood samples are needed. Placing the sensor on the skin is all that's needed. Also, optical methods pick up different blood characteristics that are more advantageous than electrocardiography. In addition, there is an abundant amount of research on PPGs that allow us to optimize our analysis algorithms. Typically, PPGs operate two types of LEDs, IR and red. The light absorption of IR and red light is different between hemoglobin and oxyhemoglobin, which are blood molecules that are either oxygenated or not. With these changes of light absorption, we can compute metrics like heart rate, saturated oxygen, and blood volume. There are two main types of PPG sensors, transmissive and reflectance. However, we choose reflectance types PPGs so the user can easily wear the device. When transmitting data, a channel represents a single PPG sensor. The characteristics of a PPG signal are shown to the right. However, we're mostly concerned with the systolic and asystolic peaks of the wave, meaning the peaks and the troughs. The heart rate is simply calculating the frequency of the systolic peak. Further, the difference between the peaks represents the AC component of the wave, while the average value between the peaks represents the DC component. By taking these ratios of AC and DC components, we can calculate the saturated oxygen.
The system architecture we implemented was a server-client relationship where we're going to have our main wearable PCB board act as a server with the microcontroller hosting that server, and with clients being a mobile application, a website, various devices, connecting to the microcontroller-based server and subscribing and listening to changes that it posts. The reason we chose that was that it was very easy to distinguish states and allow the microcontroller to control what it posts and notifies to the client. To realize our system architecture, we went with the ESP32 Pico G4 for our microcontroller. It's a very fast microcontroller, 240 megahertz, and it's also a dual-core microcontroller with some of the Bluetooth Low Energy protocol already built into the ROM. So it's a really good wireless kind of first microcontroller implementation. For our PPG sensing, we chose the MAX3105 chips. And the reason being is that those chips themselves actually pull the photodiode and very quickly at megahertz level speeds and store the data in a FIFO that we then pull with our microcontroller using I2C, which is a very nice protocol to use for our system. And we chose the MPU 6050. Which is our inertial measurement unit, so it's something that integrates our accelerometer, our gyroscope, and as well as it's got a Hall FX sensor in there to kind of do that for our filtering. And so in addition, because we're using I2C protocol and we're using multiple PPG sensors, we need to be able to multiplex our I2C bus. So we utilize this a chip called the TCA, as you can see there, the TCA 9548A, which is a I2C multiplexer that we can basically shift to connect to any given PPG sensor. So in total, we can have 8 I2C slaves on our I2C bus. And then because of some of the power requirements, which I'll get into a little bit later when we talk about the PCB design, we have a total input supply from our battery of 2 in-series 3.7 LiPo batteries to achieve 7.2 voltage, because ultimately our max chips want to receive 5 volts, but the rest of our, and draw a decent amount of current as well, while the rest of our system is running off of a 3.3 volt logic. To briefly cover how our system works, I'll cover a data flow chart. So we can see as step 1 of our data acquisition, the MAX3105 samples the actual PPG data. And then on step 2, our microcontroller pulls and receives data from the FIFO of the MAX3105. In step 3, we run a peak detection so we can obtain our heart rate. And we set an interrupt depending on other values from the IMU so we can do some pre-processing filter on the microcontroller. In step 4, we also maintain a callback server, which is used to kind of configure various settings of the number of PPG as well as the current value and what modes they're running in that we can change with connection to the client. In step 5, we actually assign the values to a BLE characteristics that notify to a client. And so step 6, it would be the ingest for the client, where the client subscribes to a specific channel to receive specific data from the microcontroller. For example, they would subscribe to read the red value of the first PPG. In our 7th, for rendering it to the actual GUI, we needed to do some buffer work, in that we have to shift it into a kind of an array window that is continually updating so that we can achieve a line graph update, which I'll get into more with the app specification. And before we started designing our PCB design, we implemented this on the breadboard, as shown in the picture on the right, with our ESP32 microcontroller on the far left, our I2C multiplexer in the middle, and the 3 red boards on the far left are our 3 breakout PPG boards. And then on top we have our IMU integrated accelerometer and gyroscope. And the breadboard implementation worked great. And this is the schematic we use for designing our PCB, and I broke it up into a couple different sections, meaning that we have our main power and filtering, because we decided to power it off of battery as well as a rechargeable battery with USB, and we use 3 linear voltage regulators, and then we have our microcontroller section as well as a battery detection circuitry and reset circuitry. We have our LiPo recharge IC. We have some, a dummy LED and other battery connections. We have a I2C multiplexer and our IMU and gyro, which and then our PPG and our level shifting down, because they all work off of 1.8 volt logic, but they want 5 volt for power and up to 50 milliamps per LED.
Our first PCB design is shown. With this design, it is apparent that it's meant. Our first PCB design is shown. With this design, it is apparent that it's meant to collect data from the foot. It is an entirely unified board with the main microcontroller area and the PPG sensors. One disadvantage of the design is that the flat surface may not be optimal for the sensors, since the foot is a curved surface. Plus, it may be uncomfortable for the user to wear. Furthermore, we found design errors regarding the reserve pins on the ESP32. The production experienced manufacturing delays due to COVID-19. On the other hand, we verified that our power management was correct. In the second version of the system, we split the board between the main microcontroller and the PPG sensor modules. This opens the possibility of switching sensors if one malfunctions, and enables replacing sensors to any desired locations. In addition, we fixed the previous design errors regarding boot and hardware issues. The second version of the system schematic is shown. Specifically, this is the schematic of the main microcontroller board. As you can see, the PPG sensors are replaced by the dual-point wire connections. There are other minor changes, including new resistors, capacitors, and new pin connections to the ESP32. This is the schematic for the PPG sensor node. The hardware is essentially the same, except for the dual-point wire connection port. Below is a comparison between the old and the new system we built. The new board includes additional test beds for easier testing and debugging. We see a radical change between the boards that greatly increase the effectiveness and reliability of the system.
We wanted our client application to be as ubiquitous yet as performant as possible, which led us to our choice of React Native as a development technology. And for those of you who aren't aware, React Native bundles assets from Android and iOS to create a cross-platform application, meaning we can write code once and potentially deploy to both Android and iOS with one app. And this is a short video demonstrating the response time of the app initial calculations, with a goal of around a 30 millisecond update rate, so that we could get about 60 frames per second performance. And this is all live stream Bluetooth data values from PPG sensors. And then this is a video of the final app working, which is in beta. And here it's going to be loading up. This is on a Note 9 running Android version 10 with about 5 gigabytes of RAM, which is important later because we have potentially a data-intensive application of streaming lots of real-time values. So here we're granting permissions on the device. And we're navigating to Insights tab, which has a lot of file selection. And here we're going to start an unrecorded section. So we have an option of starting a raw value streaming or a unrecorded or a recorded value streaming session. And this is configured right now with one PPG. And as you can see the red, the IR, and the green values. And you can see they differ by quite a lot amount, which was earlier demonstrated with our analysis of the AC and DC components of the PPG waveform. So I'm zooming in a little bit to show the actual variations as time moves along of the PPG waveform for the IR wavelength. Okay, then we're going to cancel that connection, and we're going to start it up again and do a recorded section, which I'll just let run for a little bit, and then I'll cancel it to show some of the file input-output functions of the app. And so we have our test.csv file that was generated, and we can email it out using the mailer that's selected for our UI system. And here I just have some kind of template Gmails, emails for it to go out to. And we also have, for fun, a 3D model that we'll eventually animate with some of the values for it, showing it's possible with this React Native application. And then here's the data of the test.csv file we sent to ourselves over Gmail, showing a very high density of data points, with every value on the x-axis representing 30 milliseconds. Lastly, I wanted to show that the application had been pushed in an actual beta in the Google Play Store, and as well to the iOS App Store.
A 500-second experiment was performed on one of the max chip PPG sensors. The subject, me, performed multiple breathing cycles involving deep breathing and holding the breath. This is to induce changes in the saturated oxygen of the blood. On the left hand, the max chips records the PPG signal, and on the right hand, a commercial PPG sensors measures the heart rate and oxygen saturation as a control. During the experiment, the data measured by the PPG is used to compute the predicted heart rate and the R ratio. We can then compare the ratio with the commercial sensor for accuracy. From the zoom image of the heart rate screen, we can confirm that the heart rate algorithm is accurate. On the left graph, we see the measured R ratio of the PPG sensor. The blue area represents the starting point of normal breathing in an attempt to smooth the line to a baseline. The green area represents when the subject is doing deep breathing, and the red area represents the time the subject is holding their breath. As we can see, the R ratio measured by the PPG sensor reacts to changes of breathing. On the right, we can see the saturated oxygen measured by the commercial PPG sensor. Using these sets of data, we look for a relationship between the R ratio and the saturated oxygen. The graph in the left depicts the relationship between the R ratio and the saturated oxygen. By removing the redundant 99% data points, we see there is a linear relationship between the variables. By using linear regression, we can find a function that will map the R ratio to the saturated oxygen. This is shown in the graph on the right. We can see that the derived saturated oxygen closely follows the actual saturated oxygen. This allows us to accurately measure saturated oxygen in our system. On to the budget. The total cost for a single unit is $42.55, including all the necessary components and PCB manufacturing and material costs. This was lower than we had expected, which is a win. The biggest costs are the max chip, the ESP32, and the LiPo battery, understandably so. To further optimize the system in cost, we'd require finding a cheaper PPG sensor and microcontroller. However, regarding the battery, there may not be much optimization area since powering PPG LEDs is power consumptive.
To conclude the senior design presentation, I'd like to talk a little bit about future work that could be done with this project. The first one could be taking the already designed PCB and getting a flexible PCB or a rigid flex board of it so it can implement easier into the physical structure that is chosen for it. The second could be an option that we considered for a NAND flash memory that could be on the device so that in the event that you didn't want to stream or you wanted to configure it in other ways, it could hold a variable amount of memory without requiring a connection. Additionally, we spent most of the time building kind of the infrastructure for the system and didn't have as much time to implement a lot of the kind of insight deep learning algorithms that could use for improved estimation of the feature extraction for our sensors. So that's something that can be improved a lot, whether it be on a actual client application or on a server end. Additionally, a physical design for the system is needed, and additional improvements to the client rendering process would be very good.
Thank you.